Okay, in this video we're going to go through some examples of how to use integrated rate law in order to calculate concentration of a reactant at a certain time period to try to find out how much time it takes till a concentration reaches a certain level and to look at half-life. Alright, so we're going to have three different integrated rate laws based on whether we have zero order, first order, or second order. So our first example, reaction A goes to B, so A is our reactant, has a rate constant of 2.8 times 10 to the minus 4, 1 over S, at 80 degrees. How long will it take for A to decrease from 1.85 molar to 1.24 molar? So this doesn't tell us whether we have zero order, first order, or second order straight out, but if we look at the units of K, we can tell that this is a first order reaction. So this is why units of K are important. Alright, so this is first order based on this guy right here. So we're going to look at calculating this with our first order integrated rate law. So first order has natural log, and there's several different forms of this expression. I like the one where you have A naught over AT as a ratio equals K times T. Alright, if you have the AT on top, then this would be negative in front of the K, or you can do it as the long linear version. All of them will give you the same answer. Alright, so let's fill in what we have. Ln A naught is our initial concentration, so that's where we have this information starting at 1.85 molar and going to 1.24 molar. So I put 1.85 on the top, 1.24 on the bottom, because that's the concentration we're looking for. And I'm using the rate constant that we're given, 2.8 times 10 to the minus 4 for my K, and I'm solving for T. How long does it take? So everything on the left side is a real number. We can put this into the calculator. So make sure you're familiar with natural log. So I have an ln button right here. So ln 1.85 divided by 1.24. So I get 0.4 for my ratio equals 2.8 times 10 to the minus 4 times T. So then I can divide in order to solve for T. So T is 1428.8, and this would be seconds. Okay, and the units for my time here are based on this 1 over S up here for my K. So it's measured in seconds. Alright, let's look at this second one. Reaction P goes to Q, so P is our reactant. We have an initial concentration of 2 molar, rate constant of 1.65 times 10 to the minus 3 moles per liter per second. What is P after 1,000 seconds? Alright, so what is our reaction order? We have to know that to find the right equation. Our rate constant again can tell us that. Rate constant is our K. Look at the units. So what reaction order has moles per liter per second? This unit matches rate. So that means this is a zero order. Alright, so we have a zero order reaction. So that means AT is equal to negative KT plus A naught. Alright, so that's our equation. We're just going to fill in what we have. We're looking for AT. We're given K 1.65 times 10 to the minus 3. Our T is 1,000 seconds plus 2, which is our A naught. Alright, so we've set up our equation. Now we can just do our math because we're just solving for the AT. So we have negative 0.00165 times 1,000 plus 2. So our AT is going to be 0.35 molar, because AT is a concentration. Alright, our last example, B going to C, so B is our reactant, is second order. So this one is telling you the reaction order with respect to B. If the initial concentration of B is 1.05 molar and decreases to 0.5 in 10 minutes, what is the rate constant? So this time we're solving for K. But we have second order, so let's use the right equation. So 1 over AT is equal to positive KT plus 1 over A naught. Alright, so this one's second order. We're solving for K this time, so let's fill in what we know. AT is going to be what it decreased to, which is 0.5. Don't know K. We have 10 minutes, right, plus 1 over A naught. Originally 1.05 molar was our concentration. Now, a word about units here. I put in 10 minutes for my time. That means that my K value will be measured with minutes as the time unit. You can also change this to seconds if you would prefer that. In this question, it doesn't really matter because we don't have any units that we have to match. It's just a matter of preference. Alright, so the first thing we're going to do is subtract the 1 over 1.05 over here, and then we can divide by the 10. So 1 over 0.5 minus 1 over 1.05 equals K times 10 minutes. Alright, so I put these in parentheses. 1 divided by 0.5 minus 1 divided by 1.05 gives me 1.048 equals K times 10 minutes. So divided by 10, K is 0.1048. And what would be the units if it's second order? 1 over molarity times minutes. So this is where the minutes comes in. Since I used minutes for my time, this is where it comes in with the units of K. If you switch it to seconds, then this would be 1 over molarity times seconds. Alright, so let's look at using integrated rate law with half-life. So remember, there are different half-life equations for each reaction order as well. We can use the whole integrated rate law or just the half-life equations. So we have to know the reaction order first. What is the half-life of a reaction if K is 0.015 1 over S? So again, looking at the units of K to determine a reaction order. 1 over S means first order. Alright, so let's use first order equation. So the half-life equation for first order, pretty simple. T of 1/2 is equal to ln of 2 over K. So all I need to know is K, because ln of 2 is a real number. So ln of 2 over 0.015 will give me my half-life. So ln of 2 divided by 0.015, 46.2, and since this is measured in seconds, this will be seconds. So half-life is a time unit. Alright, let's look at the second one. What is the half-life of a reaction with initial concentration of 1.1 molar? K value is 0.75 moles per liter per second. So what are the units of K? How does that tell us reaction order? Moles per liter per second. Zero order for our K. Alright, so if we look at half-life for zero order, this is A naught over 2K. Alright, so there's our equation. So we need to know our initial concentration, and we have to know K in order to solve this one. So 1.10 over 2 times 0.75 is our K value to give us our half-life. Alright, so 7.33, and this was again seconds for our units of time. So this is going to be seconds. Alright, the last one. Reaction has a half-life of 12 seconds. It is second order, so it's telling us here. Has an initial reactant concentration of 0.8. What is K? So instead of solving for half-life, we're trying to find K, but we're given half-life. So for second order, half-life is 1 over A naught times K. Alright, so if I know my half-life and I know my initial concentration, I can calculate K. So half-life is 12 seconds. Initial concentration is 0.8. And I'm trying to find K. So notice here that K is on the bottom of the fraction. So we need to get K off the bottom in order to solve for it. There are a couple ways to do this. We can do a cross-multiplying idea, or we can multiply the bottom part of this fraction over here, and I'm going to do it that way, but the point is we want to get K off the bottom. So I'm going to have 12 times 0.8 times K is equal to 1 when I multiply this over. Alright, so 12 times 0.8, 9.6 times K is equal to 1. So then I can divide. K is 0.104, and if this is second order, 1 over molarity times S, because half-life was given in seconds, initial concentration was molarity. Alright, the last one we want to look at is a course of picture example. So instead of giving us numbers, this one gives us pictures. Substance A, which is green, is our reactant, and it decomposes into substance B, which is the blue, and C, which is the yellow. And notice we still have some green left over. This is a first order reaction, so it's important to know reaction order. Okay, first order reaction. What is the rate constant? So we're trying to find K. Alright, so we have our two time points. This is time 0, where everything is reactant. This is time 30 seconds, where we have some reactant left and some product formed. Now when we use integrated rate laws, the amount of product we have is irrelevant. We can only look at reactant that's decreasing. Remember, rate laws are only based on reactant concentrations, not on product. So let's focus on the green. Since we know it's first order, we can use our integrated rate law. Alright, so here's our integrated rate law equation in order to figure out what to do. Alright, we're trying to find K, so we can solve for K here by plugging in our ratio of green balls. Since this is a ratio, the units are irrelevant. Alright, so we can use mole-to-mole ratios if we imagine that these are moles or molecules. So initially we have 8 green balls. After 30 seconds we have 4 left. So our time is going to be 30 seconds. And we can then solve for K. So we only have one variable left. So we have the ln of 8 divided by 4. And then divide by the 30 seconds. So K is 0.023, 1 over S, since this is first order. Another way we could have looked at this has to do with our half-life equation. So remember, half-life for first order is ln of 2 over K. Since we know this is a first order reaction, we actually have half-life information because we dropped from 8 to 4 in 30 seconds. So that's one half-life. So that tells us our half-life is actually 30 seconds. So we can use this equation and then solve for K. So we have multiplying by K over here to get K off the bottom, and then divide by the 30. So ln of 2 divided by 30 gives us the same K value we had before. So by using half-life information, we can also solve this fairly quickly.